Is the presentation visible?
Yes, it is visible.
Okay. Okay. So let us get started. We did take a look at some of the optimizations at a local level as well as at a global level, local level by value numbering representation of basic blocks and trying to do some constant folding, constant propagation, copy propagation, common sub expressions for that. And then we had a detailed discussion on the data flow analysis framework to analyze the opportunities for different global possibilities of optimization by formulating them in terms of data flow equations, solving them, and then carrying out the different optimization strategies. So with that, we now hope that we have our generated code modified and optimized to a good extent. And we are getting ready to generate the target code. Now, for generating the target code, the first thing that we need to decide is the use of registers. Because as you will be aware that in most of the processors, the computations that are done in the ALU will always be done in terms of the registers. So while so far we have assumed that our computing values are represented by variables, and variables will have certain binding in the memory, typically as in the stack frame or in the static area and so on. But for actually executing the program, we need to load these variables into appropriate registers, do the computation, and when the new value is ready, we need to store it back to the specific bound value of the variable to which this computed value has to go. So you can imagine that if we just do a brute force kind of code generation, that every variable that is there, x assigns say y plus z. So we load y from the memory into a register R1, load z from the memory into a register R2, compute R1 plus R2, which we may put in R1 itself, which becomes now represents the value of x. So we store R1 into the location where x should be. If we keep on doing that, then we'll see a lot of redundant load store operations happening, and the code generated target code would be extremely slow because of this overhead of redundant load store. So what we intend to do is to, while we load a value from a memory to a register and then use it, make some computations, we want to track that the value of that variable is available in the register as well as in the memory. And before it is changed further, if we need to use the value of the variable again, then we may not load it from the memory. We can use the register where it was already stored. Similarly, if a variable has been defined through certain ALU operation, the variable was residing, that computation will reside in a register. And from that point, the value of that variable will be considered to exist only in the register, but not in the memory anymore, because it has changed in terms of this computation. So we need to, register is a key resource which we need to manage in a very, very efficient manner to generate really performance efficient code. So we will introduce some of the basic issues in register allocation, and then discuss about a theoretical formulation of the register allocation problem, and provide certain algorithms for solving the problem. So this is what we are. This is our kind of outline, as you can see. So the register allocation problem is just to say that in which values in a program will reside in a register at different points of execution. This is known as a register allocation problem. So you can say that of the total set of values, the total set of variables at any point of time, what are the values which will have their copies in register? That is the allocation problem. Now, actually, for generating the code, we need something more specific, that it is not only enough to know that if there are three registers, R1, R2, and R3, and we say that variables X, Y, and Z will be in registers and all other variables will be in memory. It is not enough to just know that. We need to also know that which is the register in which X will be, or which is the register in which Y will be. Right? So that is known as register assignment problem. So obviously, if you know register assignment, you know register allocation, but not the other way around. But usually we solve both of these problems together, and they are loosely referred to as register allocation problem. So unless otherwise specifically mentioned, when we talk about register allocation, we will mean allocation as well as assignment. Okay. Now the subsequent question is, what is the unit of code or segment of code on which the register allocation will be done? Now, obviously, trying to do it over the entire program may be somewhat complicated and unnecessary. So it is done in terms of certain units of code, certain segments of code. And the typical units are of three kinds, going from least complexity to more complexity. One is certainly the basic blocks, that I can do the register allocation within the basic block, which as you can understand, since basic blocks have single entry, single exit, and has a fall through in between, register allocation problem would be much easier to solve in a basic block. But often that is too granular, too fine-grained, because if you just do it in the basic block, then as the control passes from one basic block to the other, you will not know which variables to retain in the register and which variable should be stored back, and so on and so forth. The register allocation problem done within basic blocks is called the local register allocation or local RA. The second unit, which is common, particularly in most of the languages like C++, Java, Python, and so on, are function units. Because we know that function, if I invoke a function, then it has, the currently executing function has a locality of reference. Certainly, it will either call another function where that becomes the current execution focus, or it will at some point of time return to the caller when the caller becomes a point of interest. But as long as a function is executing, it is kind of a localized unit where the computations will have to continue. And allocating registers in terms of functions is something which could be quite useful, quite efficient, and that is what is typically known as the global register allocation or global RA. However, at times we take units of code which are bigger than a function. For example, we may analyze and find that there are two functions, say f, g, and h, so that very often in the code, when f executes, it calls g, which may not be a very big function. And when that is done, f will again call h, or maybe again call g, and so on, so that it's the control is somewhat localized in terms of a few functions. Right? So I'm just saying this as a representative unit. So these kind of units can be called regions. Of course, it's not always necessarily around union of function boundaries. It could be other regions, but these are segments of code which are bigger than a function. So bigger the unit you take, naturally, your optimizations you get in terms of register allocation will be better because you are getting to know more. At the same time, it will be more complex to solve the problem because you have more number of possibilities and variabilities, right? So, but naturally, register allocation in regions will also be called global register allocation. And what we will do here is we will mostly focus on the function units, because that's the most common, and it is a no-brainer to understand that global register allocation requires a lot more time than the local register allocation. So this is the first set of issues that you have to address. Next, the question is, obviously, as you allocate registers, once you have allocated registers, then you have to do the actual code generation, which is corresponding to your 3-address instruction. You have to generate the assembly instruction, which is available for that processor, which is a processor specific stuff, which is known as instruction scheduling. Now, this instruction scheduling, if when you are choosing the instruction to represent one instruction or multiple instructions, I've given you certain glimpses of that through a simple instruction mapping table earlier. Now, when you choose the instruction, naturally, you already know the variables which are available in the register. So you have to use those registers for the respective instruction scheduling. Now, the question is, which one should you do earlier? If you do register allocation first, it will mean that you cannot move the code during scheduling, right? Because registers have all been fixed according to the flow that you have done. And while you generate the code, you may often need to move some codes around, right? Because, for example, you want to take out the loop invariant and put it outside the loop and so on and so forth. So performing register allocation restricts code movement and further optimization of the target code that you are generating. So usually it is not recommended. If you schedule the instructions first, if you do the other way, that, okay, I'll schedule the instructions and then I will, so I'll say that if I'm doing an add, I do not know whether it is R1 plus R2 going to R1, but it is some Rx plus Ry going to Rz. So if I take registers as simple variables and schedule the instructions, and then I do the register allocation. Then I finally decide which is Rx, which is Ry, which is Rz, and so on. This is better in terms of optimization, but this cannot handle the code spilling. We'll talk about code spilling more as we go through the module now. But the basic idea is when you have, suppose you have 3 registers which are holding variable values which are all required going forward. So they are kind of all live. So, and you now require a 4th variable to be used. The question is, which register do you put the 4th variable? You do not have a 4th register. So, and all these 3 values are required going forward. So what you'll have to do, you will have to choose a register, choose a particular variable residing in a register and store it back to the memory temporarily, right? So that you do not lose it, free up that register and use the 4th new variable to be loaded in that register. So this part where you know that a variable will be required in future, it is live, but still, because you have run out of registers, you are storing it in the memory, and therefore sometime in future you'll have to load it again. Is known as the spilling of the code. So as if register is a bin and that bin has got filled up and the code is spilling out of that. So once you have scheduled the instructions, you can understand that spilling needs some more codes to be put. Now, if the instructions are already scheduled, you cannot have more instructions. So if you do scheduling first, you cannot spill the code, which means that you cannot solve the register allocation problem in every case. So it's kind of becomes a chicken and egg issue overall. So what you do is you typically schedule the instruction first, do the register allocation. If you need to spill codes, you mark them and you do another pass of schedule. There's no other way. You cannot just do either this, then that kind of stuff. So that is the typical strategy which is to be followed. The other point that you have to keep in mind is register allocation is a hard problem. In fact, so is instruction scheduling. So there is always a trade-off between the speed and the quality of allocation. That is, if you, as you have understood, that if we did not do any kind of smart register allocation, we could have just done load store kind of thing and got a code running. That is the fastest you can generate a code. And if you do the totally globally optimal register allocation, you are trying to solve a hard problem, even though approximately possibly, but you will need a lot of time in doing that. So it is okay when you are doing compiled code translation, like you do in C++ or C, it is okay to spend more time in the register allocation because you are doing that offline. You are doing it in the so-called static time, and you have more time available. And you can have a good quality of allocation. But in today's time, we have several languages and several situations where we follow the JIT, just-in-time compilation. For example, we do that in Java, we do that in Python, and so on. So the entire code is not fully, the entire target code is not fully pre-generated. It is being generated while the code is running. So it is always a handshake between the code that is code of the user that is running and this part of the backend of the compiler, which is after the execution of certain instruction get to know as to what are the next instructions, what are the data types of those variables that are there. And based on that, it will have to generate the code for the next few instructions. And therefore, you are already in execution. So if you take a lot of time in deciding this, then overall performance of your execution will deteriorate because you are already in the runtime. So what you'll have to do, you'll have to sacrifice the quality of allocation. Maybe we'll go with a, in a simpler heuristic, which can be applied very speedily and fast, and go with that kind of a quality, and maybe accept more load stores to happen. And I mean, these are the basic reasons as to why JIT kind of supported languages are typically slower than totally compiled languages. But that trade-off is a big question that you'll have to answer always. And you will also have to often answer as to, do you really want to do a global allocation, register allocation in such cases, or you would be happy with the local register allocation, or you'll do a combination of those and so on. So while we talk about the basic strategies of register allocation, these are the issues that you'll have to keep in mind. And we'll try to address the problem with respect to that. Okay? So before I get into the actual problem statement, let me just stop and ask if there are any questions. Are the issues understood well? Because that is critical for understanding the solutions and the, kind of the properties of the solutions that we are talking about.
So can you explain again, sir, what happens is in just-in-time compilation?
See, just-in-time compilation is think about, say, a C language program. What you are doing all the front end, generating the intermediate code, and then we are optimizing, then we are allocating register, scheduling instruction in that iterative pass, optimizing the target code that we have generated, and you have a completely executable code available at your disposal, right?
Okay.
So while this is not just in time, this is offline, this is totally static time, right? So when you are doing that, you have a lot more time to optimize allocate registers, schedule instructions, and so on, because that is not the time when your program is executed. Now, if you think about languages, say, think about Python. When you are, so in Python, what will be the compilation? Naturally, the code is, let us assume, though Python also allows code addition during the execution, but let us, if we just forget that part, if we assume that the whole Python code is statically node at compile time, you'll be able to do the front end part. But you may not be able to generate the entire backend code, actual target code. For example, I'll just tell you one reason why you would not be able to do that. Unlike C, C++, which are statically typed, that is every variable, we have to declare what is the type, right? Whether it is a predefined type, built-in type, or it is a user-defined type, certain class structure. So once you do that, you know what are the operations that are available for that, and accordingly you can generate them. Now, Python does not need that you declare the type of a variable. That feature is not there. It is dynamically typed. What does that mean? That means that if I assign, say, the value 3 to a variable x, it will be assumed to be of integer type. And going forward from that part of the code, all integer operations will be available for x. Now, after 10 instructions, I might assign a string, say, double quote ppd to x. The same x. This is not possible in statically typed language, but here in Python it is possible. I assign a string to x. From that point onward, x becomes a string variable. So no more the integer operations are available for x, but the string operations are available for x, right? So this is the issue of dynamic typing. Now the problem is, if you are using dynamic typing, this value that I am assigning to the variable which decides the type necessarily is known only at the runtime. Because instead of assigning a constant 3 or a constant ppd to x, I could actually read that from input. It could depend on the conditional flow, the control flow in the program as to which type of value is assigned to a variable, right? So which means that statically, you do not have enough information to generate the final code. You have the intermediate representation. Up to that point only you can do. But you cannot actually, if I'm saying x plus y, you do not know what is the binding of this plus operation, whether it is integer addition of floating point numbers, or concatenation of strings, or something which is, say, overloaded, right? So which means, so how do you compile and execute? So here, in these languages, the compile and execute will go in cycles. That is, when you have enough information available at the runtime to execute to know about the bindings of the subsequent few instructions, the types of the variables, the operations that will have to be done, which are the critical things for translation. When you know that at the execution time, then you kind of suspend your own executing program code and run the compiler backend code. That compiler backend code for the next few instructions will do the final translation and generate the target code. And then you switch back, you put the compiler backend in suspension and bring back your executing program. So they are going in the handshaking mode. So that kind of compilation strategy is called as just in time. Why is it just in time? Because you are not pre-compiling the entire code. You pre-compile as much as is possible statically. But because of the dynamic typing, when the code is executing, you get to know how much, exactly what needs to be translated. and you compile it at that point, just in the time when you need that code to be compiled. So that is called GIT, which is a strategy which primarily evolved with Java. And so naturally there are certain consequences of that. When you do that, typically these languages which are dynamically typed needs a runtime system to work with that, which is known as a virtual machine. So often you do not translate to the physical processor instructions, but you translate to a virtual machine instructions. So Java has a JVM, Python has a PVM, and so on. Those are added stories. But this is the basic issue of going in cycles to execute, compile, which is not there for the statically typed languages. You compile and then you execute till you want to make change and compile. Actually, this JIT, execute compile cycle, gives you the ability that you can also add instructions during execution, which you cannot think of in languages like C. Right? But in Python, you can add instructions while the program is already in execution. Right? Because you can add instruction till it becomes due to execute that instruction. Because if you add instruction, what you'll have to do? For once, after addition, you will have to run the front end during the execution time so that you get the intermediate. And then subsequently, again, you are just doing the back end and generating the code. Right? Does that explain the basic concept and issue?
Yes, sir.
Right. So once you understand this difference, you will understand that register allocation and instruction scheduling becomes very, sensitive to the time you spent on them. Because if you do now it's a big trade-off. Why are you doing an optimal register allocation and instruction scheduling? So that your code can be fast. Right? For a statically typed language, it is a one-way process. You can spend the entire time available to you to compile, optimize, get the best allocation, and so on. In the GIT mode, you are using the part of the execution time to do this task. So if you optimize very well, subsequently the code will be faster. But the time taken to optimize will also add up to the execution time, because that's what the user gets to see. User does not get to see as to how much time you have actually executed Bahar code and how much time you have spent on doing this GIT compilation. So there is always a question of trade-off. If you do not do allocation at all, I mean, you will have to do, not you cannot do at all, but if you do it in a very rudimentary way, then in many cases, the code will become very slow. If you try to do it in a very sophisticated way, you will spend so much time that your code will become slow. So there is a trade-off between the speed and quality of solution that we provide in terms of allocation and instruction scheduling optimization. Right. So that was the basic point I was trying to drive in. We will not be able to do much of the GIT style, but it is good to be conscious about these issues. And if there are no other questions, then I'll go ahead and start defining the problem. Any other question, friends? No. So let me go back and continue. Okay, so I'm back on that slide 10. So we are trying to define an instance of the problem in a somewhat formal way. So we said that basic blocks, right? And as I said, usually at a function level. So we formulate a decision problem related to register allocation. I'm sure you are familiar with decision problems, which are often work hand in hand with the optimization problem. So in the optimization problem, for example, I could have asked that given the code, what is the minimum number of registers to ensure that there is no conflict and there is no extra load stored and so on. So that will be an optimization problem, which are difficult to deal with, particularly if you have to talk about hardness. So what you do, you form a decision problem where the answer is always yes or no, true or false. And it is easy to show that if you have a solution to the decision problem, then in polynomial time, you will have a solution to the optimization problem as well. So it serves the purpose. So what is the decision problem? You are given with the intermediate language representation of the program, which is in terms of the control flow graph. And you are given with a fixed number k, which is the number of registers that you want to use. So you have to make an assignment of registers to program variables in such a way that these three conditions have to be satisfied. One, no conflicting variables are assigned the same register. Right? That is, what are conflicting variables? Conflicting variables are those two variables x and y are conflicting if there is some program point, at least one program point, where both of them are live at the same time. If both of them are live, naturally they cannot be assigned the same register because one will erase the other. So there has to be no conflicting variable assigned the same register. Second is the cost function. So the first you can say is a constraint. Third also is a constraint that you cannot use more than k registers. So these are the two constraints of the optimization problem that you are converting into the decision. And the second is the cost function, which says that no extra load or store are introduced. Now, naturally, some load and store will have to be introduced because initially registers do not have anything. Everything is in the memory binding in the stack frames, let's say. Even if we assume that static and dynamic, all those are not there, to just simplify the problem. So there will have to be load stores, but there is no extra load or store is introduced in the register allocation. So that is the cost to minimize. Now, if you satisfy these conditions and the answer to the problem is true, then you say that the problem, you say that the register allocation is solved, it can be done. And if it is false, you say it cannot be done. K registers cannot satisfy these conditions. So the problem to the decision problem turns out to be false. And therefore, you can very easily convert this to the optimization. All that you need to do is to start with k is equal to 1, k is equal to 2, k is equal to 3, and so on. And the minimum value of k for which the decision problem returns true, is a solution to the optimization problem. Now, this decision problem, long back, more than 50 years back, was shown to be NP-hard by Sethi. You know Sethi as the author of the Dragon Book, Aho Sethi. Now, since it is NP-hard, which means that there is no known polynomial time algorithm to solve this problem. And therefore, you will have to use certain heuristics to solve the problem. So as we will see, that we will convert this problem into the graph coloring problem, which is also NP-hard. But then we'll use a graph coloring heuristics, certain heuristic approximate solution for the graph coloring, and map it back to the register allocation problem. And it often gives you quite a good result. But there are simpler heuristics also, simpler strategies also. So we'll start with the simple heuristics and then move on to the graph coloring approach. Now, formally stating about conflicting variables, two variables interfere or conflict if their live ranges intersect. So we had illustrated live ranges earlier. Just to recapitulate, a variable is live at a point P in the flow graph if there is a use of that variable in the path from P to the end of the flow graph. On some path somewhere, there's a use of this variable without being redefined. So that the variable is live, and live range is the smallest set of program points in which it is live. Smallest because we want to be, we want to have minimum amount of constraints. So now if two variables live range intersect, that means that there is at least one program point where both of them are live at the same time. And these are called the conflicting variables. Now, how do we represent a program point? It is easy. Every program point will belong to some basic block. So we put the number of the basic block and we put the instruction number, the serial instruction number in the basic block. So this doublet will uniquely define every program point in the program, and we'll be able to see whether their live ranges are intersecting or not. On to slide 8. This is just a very rudimentary example. So what you have is if condition. On the left, if you just see the code is if condition, some condition, then A is assigned a value, else B is assigned a value. And then again, there's another condition where if the condition is true, then value of A is used in some computation, otherwise value of B is used in some computation. So if you put it in terms of the control flow graph, this is what you'll get. If condition true, then A is assigned a value, false, B is assigned a value. Then both of these controls converge, merge at B4, where you again check the condition, go to B5 or B6, use A or use B. So what is the live range of A? Naturally, the live range will start when you first define it. So it starts at the definition of A in block B2. And how far it is live, I can see that from this point, I can go to B4, go to B5, and there is a use of A. So A will have to be live when it comes out of B2 because B5 uses it. A will be live when it enters B4, and it will again have to come out live when it has to go to B5. So along this path, I can see that A will have to be live over B2, B4, B5, which is a live range of A. Similarly, of course, it does not need to be live over B2, B4, B6 because B6 does not use A. So B6 does not require A to be live. Live range of B will be B3 is when it is defined. It is used in B6 before another definition. So it has to be live along up to B6. So B3, B4, B6 is the live range of B. So that is how, if you really want to conceptualize it on the control flow graph, this is how it works. So let us have the first strategy. So the first strategy has two parts. One is we will neither restrict to basic blocks, nor we will restrict to go as big as function. Rather, we will allocate registers for variable that are used within a loop. So we will identify a loop. A loop naturally can have multiple basic blocks. So we will identify a loop, and in that loop, we will try to allocate registers. This is a kind of a, you can say, is a very common greedy heuristics, because you always try to focus more on the loops because you expect the loops to run multiple times, several times, usually. Right? So anything that you optimize for the loop will give you better returns than anything which is on the fall through code. Okay? Naturally, what you require information about liveness because you have to do it by the live ranges. So you require the information about liveness of variables at the entry and exit of each basic block of the loop. So you cut out the loop and also provide the information of liveness, which we have already discussed how to set up a data flow analysis framework to compute the liveness. So you have executed that, and you know the live variables at the entry and exit of each basic block. Now, what you observe is once you have computed a variable in a register, you will try to keep that in the register until the end of the basic block, if there is some subsequent next use of that variable. Right? And you also assume that load store instructions cost 2 units, because it's typically, in terms of program execution time, the maximum time is goes in the memory fetch. So load store instructions have 1 unit of the instruction and 1 unit for the address. So at least 2 units of cost will be there in the load store. So you assume that load store instructions have cost of 2 units. You can make it more sophisticated, but this is just a rudimentary simple algorithm which gives you a quick result. Now, what you do on slide 10, for every usage of a variable v in the basic block, until it is first defined. Once it is defined, naturally it is in a register in that basic block, and its subsequent use will not need anything. But until it is first defined, if it is used, then you are obviously saving some cost. So you say that that unit of cost you consider as 1. I mean, how many savings did you have? So till it is first defined, naturally the variable will have to be live on entry to basic block. Otherwise, you could not have used it without defining it. Now, you increment the savings by 1. And after v is defined, it stays in the register anyway. So all further references will be to that register. So you don't add anything. The second, for every variable v which is computed in a basic block. Now, and if it is live on exit, that is, you have computed a variable in the basic block, and when you are going out of the basic block, it is still live. So you will count a savings of 2 on that variable, because if that variable resides in the register, then on exit, you will not have to store that variable. Otherwise, since it is live going out of the basic block, you will have to do a store. So if you can allocate this variable to a register, you will save 2 units if it is computed in the basic block and is live on exit. Right? So these are the 2 components of the cost. One is how much you save by not having to get it at the very beginning before its definition, and one is how much you save by computing and being live on exit. So the total savings for a variable v over the loop is the variable, the loop has multiple basic blocks. So for every basic block, you compute the savings for v, and for every basic block, you compute this predicate. Live and computed is a predicate, because it will be 1 if v has been computed in this basic block and is live on exit. If v has not been computed, or if it is not live on exit, then this cost will not be incurred. So this is a predicate which actually is to be multiplied by 2. So we put this predicate as 1 and 0, 1 or 0. So this is the cost function. This is rather the savings function. You are looking at it from the reverse point of view. This is a savings function for the variable v in basic block b of the loop. And you do that for every basic block in the loop and add up the total. So then rest of it is simple, that whichever variables will have the highest savings, they will be put to the register. Now, there may be a certain one-time load store on entry exit of the basic block, which we ignore because they're just one time at the beginning of the loop. I mean, when you start the loop, obviously there'll be some loads, and when you end the loop, there'll be some stores. But those parts we ignore, because the loop is expected to iterate multiple times, and it will enter and exit only once. So those 2 units we example, right? So here is a loop which has 4 basic blocks: B1, B2, B3, B4, And the DFA for liveness has also been done. So at the entry of every basic block, we show what are the variables that are live. So B, C, and F are live on B1, on entry to B1. ACDF is live on entry to B2, and so on. Right? And these are all shown as to what is the liveness. So you have the whole of that coming in. And you can see that after B4, the BCF will have to be live for entry to B1. And the other part, similarly, the other part from B3, these are the two exits from the loop that are possible. And whatever corresponding basic blocks they go to, we are showing what is the requirement of liveness of variables for those. Right? Now let us analyze one by one. So let's say first take the variable A. So A is being defined before being used. Okay? So A is not used without definition. In fact, A is not live, so it cannot happen either. Therefore, if you look at the table below in the row of A, the first entry, savings part is 0. There is no savings to get by having A in a register. What happens on exit? A has been defined in B1, and on exit, A is live. Actually, it is live on both these. It would have been enough to be live on only one. So I gain 2 units if I can retain A in a register. So the live and computed predicate is 1, and I have a cost of 2, savings of 2 here. Let's look at A in block B2. A is used here. It comes in as live and used here in A minus F without being defined. So I have a savings of 1. It has only one use, so I have a savings of 1. As it goes out, A has not been defined and also is not live going out of B2. So the live and computed predicate is false. It is 0. Similarly, in B3, A is used before being defined. So I get a savings of 1. And it is not defined here in B3. Therefore, I do not get a savings in terms of the live and computed. In B4, A is neither defined nor used. So that cost is 0. So you have a total of 2 plus 1 plus 1, savings of 4 if you keep A in a register. Let's look at another, say B. B is live on entry to B1. So, and B is used 3 times before being defined. It's actually not defined at all. So B has a savings of 3. Now B is neither live nor defined in B1, neither live on exit nor defined in B1. So the live and computed predicate is false. You get a 0, 3 plus 0. In B2, B is not there. You get 0 plus 0. In B3, it's not there. You get 0 plus 0. In B4,
Sir,
B
in
is
B2,
yeah,
it's defined.
but it's not live going out. It is defined. 2 conditions. It has to be defined and it must be live. If it is not live on exit, then I do not gain anything by keeping it in the register, retaining it in the register. I'm trying to do the register for the entire loop, not only for this block. Are you getting that? So in case of A in B1, I counted live and computed to be true because A is defined as well as it is live on exit. Here, B is defined, but it is not live on exit. So I don't need to remember A. I don't get any benefit by remembering B in a register. So the live and computed in B2 is 0. Similarly, in B3, it does not participate. In B4, just see the contrast here from B2 to B4. In B4 also B is defined. B2 also B is defined. But in B4, it is live on exit. So I will gain 2 units if I keep it in a register. So the live and computed is true and I get 2 units here. whereas I don't get that in V2. And if I add up, I get the total savings of 5. Right. So we have to keep doing this. Let's do a final one. Let's do F. So F is live on entry to B1 and is used before being defined. So I get a savings of 1. It is not defined in B1. So live and computed is false. In B2, again, I get a savings of 1 because it is not defined but used live on entry. Live and computed is false. In B3, it is defined. It is not used before being defined. So savings is 0, but it is defined and it's live on exit. So I get an advantage of live and computed being true. I get 2. And in B4, it is not defined. Neither it is used. So I get 0. So total is 4. So in this way, for all the 6 variables, we get the savings that are possible. Now, depending on the number of registers, I will pick up those many highest number of savings. So if there are 3 registers, then obviously B will be the first choice because it has 5. And I have 3 variables A, D, and F having the cost 4. So I'll pick up any 2 of them. That is arbitrary. So here I've marked just showing that it is A, B, D. But if I had 4 registers, I will take A, B, D, F. If I had 2 registers, I will take B and any one of A, D, or F. Right? So, I mean, this is a simple heuristics, but often works out to be optimal or very close to the optimal. Right? So that's a single loop. Now, so to complete the analysis of loops, all that you need to do is to extend it for the outer, nested loops. So let me just show the diagram. So you have a nested loop L2 here with the body and you're looping. L1 does something, goes into L2, loops for sometimes, comes out and loops again. So obviously there are possibilities that the variables X, Y, and Z kind of say, which are assigned registers in L2, but not in L1. Right? If that is the case, then you'll have to load X, Y, Z on entry to L2 and store them back with you, because you need those variables in the register in L2. Similarly, there could be variables A, B, C, kind of, which are assigned registers in L1, but not in L2. If that is the case, then you'll have to store those variables before you enter L2 to make the registers free and load them back as you get out of L2. And there could be variables PQ, which are assigned registers in both L1 and L2 or in none of them. So there you don't need to do any separate action. So if you do a single loop based register allocation and then append it by this observations on load store, you add those load store, you have a quick and dirty solution for the loops, optimizations of loops in terms of the global allocation. Right? So I think it's time. So I'll stop here quickly. If there is any question, I'll take. So this was just a very quick and dirty rough heuristics, which is very easy and quick to execute, except for the liveness of DFA, which will have to be done in any case for such cases. But after that, it is a quick and dirty solution, which gives you a fairly good solution in most cases. Next, we will look into the graph coloring approach, the Chaitin's algorithm, tomorrow. Any questions, friends? No. Okay. Thank you then very much. See you tomorrow.